Hello, this is Charles.
Okay. Oh, hi.
Hi.
Actually, I just need the fix again for this graphics bug, the performance goal bug. Could you send that to me again, please? Do you understand what I'm asking?
Yes, it was to set up performance goes to speed in the notebook.
I'm aware of that, but you had an internal fix for existing
Oh,
graphics, right?
right. Let's see.
Okay, I can find it in my email archive if you can't find it, but I want to get going on some other things here. So, an automatic will work correctly, right?
No, we just support speed and quality.
So, what will it do if I say automatic?
Um, well, I don't remember the code. Probably disregard it and
Well, that's not right. So you should make it do something definite there. Make sense? Because that's how it
yes.
works by default in every other function. Okay, anyway, I was going to introduce this live stream.
I just sent the code in the chat.
Okay, you need to send it to me by email, please,
Oh, by email. Yep, sorry.
because my Zoom system is broken and I can't get to the chat. Again, I asked about that.
Okay, done.
Okay, all right. Okay, thanks, Charles. I think that's what we need.
Bye.
Bye. Okay, for people joining this live stream, we are looking at various instances of multiway systems, particularly, let's start at the beginning again. Okay, we got kind of derailed there. We're looking at multiway systems from various kinds of non-deterministic systems, basically to get intuition about how multiway systems work in the case of things like quantum mechanics. And here we're looking particularly at non-deterministic Turing machines. And what I had started to do here was to look at the case of Turing machines that have a total of 3 rules in their um, um, in their rule set, and those 3 rules in may overlap or may not. So sometimes those rules will contain um, uh, oh my gosh, not this problem again. This is such a stupid problem. This is some kind of problem with the way that the parallel network I have is set up. Okay, so in any case, what we're looking at here is Turing machines, and also we were supposed to have from Mano material. I think she'd sent some stuff, but I don't know where it is, so it doesn't really help me very much.
She should be here very soon.
Well, I understand. Oh, shoot. We should have set this to use, because of this bug, we have to set this to use performance goal arrow speed, or what's happening, which is the notebook is just slowing down to a crawl here. So I need to rerun this. And if you notice me running this thing again with multi-way Turing machine, I got to rerun it with this option so that we don't put all kinds of stupid dynamic things into the graphics. Okay, do you understand, Ed? Ed, do
Yes,
you
I do.
understand? Okay.
Yeah.
Okay. And let's see. Parmenides on our live stream is asking about non-deterministic Turing machines, canonical quantum gravity, homotopy type theory. Yes, these are all relevant. And it's also relevant to understand if you are an observer in a system that is branching, and you, with your sort of observer brain, are also branching, how do you perceive the branching system? It's similar to the issue of if you're an observer embedded in a system, you only get to be sensitive to the causal graph. And I think there's an analogous thing here relating to branching and multi-way causal graphs. But right now I'm just studying kind of the phenomenology of non-deterministic Turing machines. And what we're seeing is this is the multi-way graph, and this thing here is another indication of what the Turing machine is doing. This is basically just showing it's a more spatially oriented representation of what the Turing machine is doing. And I'd love to get a different representation that that can merge these two things. But the first thing I was doing, so most of these are pretty boring. Their multi-way graphs just show a tree. But in this case, that tree will be representing the head going to all these different positions. And I don't know, maybe we can represent this by having paths that show how a head goes from here to there and so on. Am I making sense? Do you understand what I'm saying? Ed, are you on here or not?
Yes, I'm here.
Do you understand what I'm saying or not? No. Okay.
I'm also trying to get my internet service fixed, so I'm slightly distracted.
Okay. Maybe we should not do this live stream at this time. I think this may be a doomed live stream. You know what? I think we should. Well, maybe I'll just do this on my own. Okay.
Okay.
What does the okay mean? Does that mean you've solved the problem, or?
I've given up on it. I'm just going to pay attention to this.
Okay. Good. Thank you. Okay. So do you understand what I was saying or not? We're trying to trace, this is a multi-way graph that shows where each node is a complete state of the Turing machine. This is a more detailed picture showing the collection of states that the Turing machine gets into superimposed on each other. Do you understand what I'm saying?
That seems clear.
Right. But so what I'm trying to say is if we want to combine those two, we want to know if the head is in this position, it could go to that position, but not to this position, and so on. Do you understand what I'm saying?
Let's look at a more complicated one.
Well, there aren't very many more complicated ones here.
I'm having trouble connecting to the internet. Take a look at the help section in your Alexa app.
I mean, I don't know, something like this is a different kind of thing.
Right.
So in other words, where this is saying it branches. So I don't understand what that branching is doing with respect to that state. Okay, so let's take a look here, for example, at that. So let's take a look. That's the rule. Okay, so we notice here, unfortunately, I don't seem to, do we have Mano here yet?
Mano's previous meeting is running over. Getting a new team now.
Okay. I asked for a very specific thing. I needed a very specific piece of code, and whatever. Okay, you know what? Okay, you know what? I'm just going to use this. So I think this will work now. Let's see if this does work. Nope. Maybe it will work if I say this. Oh, for goodness sake. Oh, that's a flop. That wasn't the spec, but I guess that will work. Okay, so we see that in this state, it has two possible things it can do. Am I making sense?
Yes.
Okay, so let's look at, we could just look at the multiway graph that we get from this. So here, let's get rid of those, and let's put in this particular rule. I think that rule, I think we need all of those. Oops. I think I need that whole thing there. I need that rule. Now we need this with t equals 5, for example. Oh, I want this now. Oh no, not this problem again. Oh, not this again. This is broken. Okay, so Mano's code there has broken this. What this should have shown, okay, so we need to point that out and get that fixed. This should have shown the actual states, but it's broken here.
I've sent her a screenshot.
Okay, thank you. Okay, we're not doing well today. Let's all right, let me show what we get from multi-way Turing graphics here.
Hello.
Hi. Well, we found some breakage in your code, and I'm pretty confused. So this is this in Dropbox somewhere, or is this just a thing you sent me by email? Or is this something submitted to the function repository, or what's its story?
You can find the most recent version
Okay.
under physics and the folder mono.
It's good to hear a more refined version of your... Oh, wait a minute, that's not the right place for it. It should be under code development.
Okay.
Okay, I'm going to move it right there right now.
Okay.
Okay, so that code of yours now breaks the state rendering function of multi-way Turing machine. Do you understand what I'm saying?
Yeah, we were facing this problem with okay, I see what's happening.
How do I fix it?
I'm not sure. Let me take a screenshot and try to see if I can find a way to make it work.
Okay. So if I run this, okay, wait a minute. Is this different from what, okay, you'd sent me something by email. This is now different. Is that correct?
I thought I sent you this.
Okay, but whatever. Okay, all right, fine. It looks different here. For example, this single row and single heads thing, which you added this thing here. Is that right? Which is my Turing machine plot.
Yeah.
Okay, so is that the thing that was without a third argument or not?
Yeah, it doesn't have a third argument. I just made it so that it can accept options from array plot.
Okay, but it needs to know the S and K values again, right? Otherwise, it's going to plot the thing incorrectly. Do you understand what I'm saying? It's not going to have the right range of colors if it doesn't know the total number of colors. So you
Right.
need to have S and K in there, just like we talked about. Okay. Okay. So this multiway, okay, so here we go. This is my attempt to average over multiple states here. Okay, so this is taking, do you understand, Ed? Do you understand what this is doing? Mano, do you understand what this is doing? This is taking all the Turing machine results. Okay, so for example, here, it's taking, if I say this, t equals 3 or something, it's got all of those things. Those correspond to Turing machine states. Is that making sense to you?
Right, it's the average tape at that level.
It's the average tape. And what I didn't do, and Mano, I wanted you to do, is to put in little, tentacles here that represent the head state, right? Because this is just saying where the head is. It's not representing what state the head is in. But the head would have, in this particular case, it would have a head up location, a head down location, and those should be in different gray levels to represent their different, the different probabilities of the head being up and down.
Yeah, okay. That makes sense.
I didn't, and I think you should make the overall color of the head here be the total probability, and then each one is I mean, maybe we can use colors to represent these things better. Not sure what the right thing to do there is. I mean, maybe what we want to do is maybe we want to slice this thing in S pie slices, and then have each pie slice starting from the middle be the color level corresponding to the probability of that state. Do you see what I'm saying? So the average color of the whole thing will be the average, will give you the fraction of time the thing is at that location, but then essentially the weighting will tell you what the orientation of the head is. Does that make sense?
Can you repeat that one more time so I can make a note?
Okay, so what I'm saying is, with the way the head usually looks, it has a pointer pointing in some direction, right?
Mm-hmm.
You understand that? So let's say it's pointing up and down, up or down. Then what I'm suggesting is you slice the pointer in two, and the top half has a gray level that corresponds to the probability that the head is both in that location and in that state. Do you see what I'm saying?
Okay.
Right? And the point that I'm making is, what you're seeing here is the probability that the head is at this location is 0, so it's white. There's no head here. But what I'm saying is, with the procedure I'm proposing, I believe that the average color, if you look from a long way away, averaged over the head orientation will be the correct total probability that the head is in that position. Do you see what I'm saying?
I'm having a little trouble.
Okay, so you have to think through, how am I making these colors, right? What this is doing is it's asking, each one of these things has the head in a particular location, right? What is that color? That color is taking, in a sense, unit probability for the head to be somewhere, and saying, what's the probability that the head is in this particular location? At least that's what I think I'm doing. I may not be doing it correctly, but that's what I think I'm doing. So at some point, the gray level, I mean, I'm not sure this is what I'm actually doing. It's what I should be doing. The gray level will be spread uniformly across all these points. Okay?
Yes.
Although that may not be the right thing to do, because maybe they'll get too light if we do that. Do you understand what I'm saying?
Yeah.
So what I'm saying is, if we're representing both the position and the orientation, I'm just describing what the gray level should be to get that correct. But I want to keep going here because let's look at what I'm actually doing here. So I've got a key value map. What did I do here? Okay, so this is on counts over length. Right, so this is in fact correct. It is uniformly distributing gray level. So in other words, if the head can be at any one of these locations with equal probability, although this one looks like it's sort of playing the Gaussian thing, this looks like it's like a Galton board where the head is going, right? You get what I'm saying, making a binomial distribution here, right? So it's probably more concentrated in the center, and we see that both in the tape. Because there's more concentrated, color 1 in the middle of the tape. Okay, so let's keep going. And what I wanted to do was to make, the first thing I wanted to do was to make a Monte Carlo way of computing, because right now this is a very expensive computation. To work out the color out here, even though it's very light gray, we're having to enumerate all possible paths. Am I making sense?
Right.
Okay, so if we go down here, first step. Okay, so this is getting all the possible paths. Now, what we want to do, actually, if we do in the multiway evolution, if we use random ordering, how does that work? The event selection function, do you remember how that works?
Looking it up.
I think we might be able to say, if we're very lucky, we might be able to say random 3 or something. Interesting. Okay. So let's say we say random 10 here, and let's say we go much larger number of steps. T equals 10, for example. And now we do our Turing machine plot of this, right? Which we should Turing machine plot of that thing there. Okay. So this is what we get when we have random choices at each step. So now if we were to have if we were to follow all the paths, we get that, and that's not a very good approximation. Okay, so what did we do wrong here? So that's kind of the Monte Carlo version, because at every step we're picking 10 random choices. Am I making sense?
Right.
Okay, so let's keep going. I mean, I don't understand what this is going to be doing for us. So let's say we pick 30 random choices. Let's see whether we get a better approximation. We do, but it's still not great. Okay, so my question is, how do we get this? How do we get a good approximation here? I'm actually very surprised that this is not converging better. Ed, do you understand what this is doing?
I'm looking at how many total cases are there? Is it what, 2 to the 10 if there's?
Well, let's find out. Okay, so let's say we just want to do in here, and as I recall, this is called in that case T comma states counts list.
Let's change that T to like 3 or something small.
Well, no, I'm showing you the number of states in the multiway graph, right? So if I say up to 15 steps, this might take forever. Okay, no, it doesn't take that long. So let's find out what this is. Let's see what this is. Is this a quadratically growing? Yeah, it's a quadratically growing thing. So I think what's happening there, in this case, states are merging. And it's not surprising. States are merging. So if we were to look at the graph for this case, okay, that would have, let's see. Let's see, what do I want to call this? It's states graph structure. And remember the thing we're not supposed to forget, performance goal goes to speed. Okay, what is that now? So that is the multi-way graph, and let's do that as a layered plot. Let's see, layered digraph embedding. Okay, do you understand that? So that's the multi-way graph that represents, that's starting off from the initial state. That's, head goes one way, head goes the other way. Let's remind ourselves what this rule actually is. And Mano, your Turing machine plot with rule plot needs to have this flattened, which shouldn't be the case.
Okay, I'll make a note.
It looks like each of these hits a tape configuration that will repeat forever.
Oh, why did this not work? Oh, because I've got to give the 2-2 thing here. Wait a minute, what are you saying there? I see what you're saying. That those. So this is then misleading, because many of the cases here, in other words, we've conflated all the cases that have for a given time step together here. And in fact, what's happening is that some of those cases are very independent of each other.
Right.
Richard is suggesting our Monte Carlo needs importance sampling. I think that's what it's getting. I think the problem is that in the multi-way graph, there's a certain amount of merging here. Well, the case, let me see if I can run this case here.
And maybe we should do a merging of all the tapes. The union of all possible tapes might be more instructive than the average.
What do you mean union?
If it looks like there's only 10 possible tapes after 15 steps.
I see what you're saying. All right, let's look at that. Let's look at that. Okay, so let's look at this. Okay, so we want to get okay, so let's go 5 steps here, and let's get all the possible configurations. Did I goof something up? No, there we go. Okay, so they're all the possible configurations. Now, what you're saying is, should I ignore the head position?
Yes, I'd say just look at the final tape, all the possible final tapes.
Well, I don't know what you mean by final, because I mean these tapes are, so each one of these, let's look at the structure here. So here what we've got is for each step, we're mapping, last/at hash, we're mapping that over this. Oops, what am I doing wrong here? I am confused here. What?
You need to go one level in.
from what? Why isn't this last here? Hold on, what does that look like? Oh, nothing to do with that. That ridiculous horror. Which we got to fix, Mano.
Mhm.
Okay, so those are the collections of tapes. So maybe what we can do to get a sense of what's going on is do a counts on each of those. So that shows us the number of times each tape occurs. Maybe we want a reverse sort here. So that's saying that certain tapes. Okay, so this particular tape, the all blank tape, occurs 13 times, but these other ones occur just once. Does that help you?
Yeah. Try taking that last set, remove the zeros, and do the average of the rest.
What do you mean remove the zeros?
Well, I guess we can leave that in.
No, I don't understand what you mean by remove the zeros. I mean, so what you're saying is
Or remove
of
the all
count.
zero tape instead of averaging the all zero tape in.
I don't think it's going to make much difference. I mean, we can't remove the all zero tape because then we'd have no tape at all in the first step.
Right. That last one, that's not looking as balanced as the ones we had before. I think that's more instructive. These look quite different.
But that's this, isn't it? That's exactly what I'm computing here. That's what the orange is. The orange is nothing other than this average tape.
I see. Okay.
I mean, and here, if we go, let's say 12 steps or something, and I say array plot of that, I should get. Okay, now I'm a little bit confused by this. Why is this a one-sided thing like that? Do you understand that?
No.
Did my averaging work correctly? Because I think I'm doing exactly the same computation here.
It looks the same.
All right, let's go and say 8 steps. Let's not do that. I'm confused. Unless there's some goofy thing. Okay, so let's look at my code for doing this here, this Turing machine plot code, which is this code over here. I think Nano has modified this a bit, but this is single row. Right, that's what I'm computing here, is the single row thing, which is mean last / at list, which is exactly the same thing we're now computing, right? Am I making sense?
Yeah.
Okay, so what went wrong here? I don't understand why this is 1/9, 1/9. What on earth is going on here? Is there some...
Oh, maybe it's the reverse sort.
Completely crazy. Thank you. Thank you. That was just completely bonkers to have that there. Yeah, bonkers. The reverse sort.
Oh, it makes sense to sort the tapes, but not to sort the results of the tapes.
Yeah, right. Okay, that's the picture we expected. And if we now do, I mean, just to be clear what this is going to look like, if we now do, let's say, list plot 3D of that. Okay. Let's actually run it a little bit longer. Is there list step plot 3D? Is there a way to make this in steps? I think if we say interpolation order to 0. Okay, and now what do we want to do? Now we want to say, do you know how to make the side walls there? Well, let's say,
I don't. I'd need to look it up.
it's kind of got faux side walls. Okay, so that's now the distribution, the probability distribution to find for the value on this tape, as opposed to the probability distribution for the head position, which we can also compute. So let's just do a little bit bigger case of this. Okay. Dandy. All right, so that's a very nice regular looking thing. Okay. Interestingly, that's not your average binomial distribution. It's something slightly different. So let's do, for this particular one, let's also compute head position. Let's compute the probability for different head positions. And let's see, how do we do that? So what we want to do there is exactly what I did here. Let's see, what's the best way to compute this? I want to just say, I basically want to get a sparse array, and then I want to turn it into a non-sparse array. Am I making sense? So
It seems like the normal thing to do.
okay, so let's take this. Oh no, let's take this part here, and then we want to get the head positions from this. Head position is the second element of each one. So instead of mapping last, we want to say map hash sub 1, 2 onto 2 expression of hash. Okay, mapping that onto these. Did I get this wrong? I think I don't need that. Okay. All right, so those are the head positions, right? So now for those, what I want to do is for each of those, I want the counts of those head positions. So let's take the last one of these.
The min-max increases backwards.
What? I mean, the min-max is just the bounding area. Okay, so look, this is, hold on a second. Let's just take, this is, that's the position, that's the number of counts. So in a sense, what we want to do is we want to say normal of sparse array. Do sparse arrays take associations of that? Ah, okay. Well, this will certainly work. Of normal of %191. Okay. That gives us the positions. Okay, so let's take this, and that goes into here. So this is going to be counts of that. All right, I claim those are that's the density of each head position. Okay, so let's make the same kind of plot we have here for the density of the head position. What? Wait a minute. Oh, there's another issue. The issue is that these are not, we have to be adding to the sparse array. We have to tell the sparse array the range of coordinates that we're taking. So this needs to be in that sparse array, right? Do you understand what I'm saying? We need to say length of last of two expression I think this will work. Okay, do you understand what I'm trying to do? I'm trying to make sure that the sparse array actually is as long enough. Do you see what I'm saying? To include, because these head positions don't necessarily include all of the tape locations that we're listing.
Right.
Right. The way I usually do these is
There we go.
I'll find the bounds, and then I'll add the range to everything, and then I subtract the range, and that way.
I think I have a simpler solution here, he says. Maybe. Okay, so let's go to 14 steps then. And let's see. Okay, so that's the head position in this case. And that's kind of interesting. I mean, so the head position is kind of linear, and this one is kind of quadratic. Right?
Yes.
Okay, so that's the density of head positions there. Now.
And you beat my algorithm in 1 second.
What's that?
You beat out my algorithm in 1 second.
Which algorithm?
Oh, the one I was explaining. He said, "Oh, I've got something better." And then, right, boom, it works.
Yeah. Okay, so let's go back up here and look for any of these other rules that we think does something interesting, because we looked at that last time, although we got very gummed up with the whole crazy. I mean, let's take this one here, for example. Don't know whether that's going to do anything very interesting. I don't think any of these are going to do anything profoundly interesting, although this, remember, is from a blank tape, and we have to look at what happens from non-blank tapes. Well, actually, that one looks mildly interesting. I'm gonna pick up this one instead, and take a second example here.
Well, it doesn't matter if you start with a blank tape, because after a step, you have a mixture of blank and non-blank tapes.
Interesting claim. That's an interesting claim. Okay, let's look at this guy, and what we want to look at. So first of all, let's just look at it. Well, actually, let's first of all say Turing machine plot of that, comma, oh, we got to flatten it, 2-2 rule plot. Okay, so that's what it's doing. Okay, so now let's take a look at what it okay, it's pretty boring. Now, I wish we could actually see the states here, because then we'd understand what was happening here. But last time, we had started looking at, let's look at this kind of indicator here, but let's do it for the next level up. And let's, okay, so what this is doing, okay, so let's do 4 cases in the rule. Okay, so now I believe this is generating that with that. Okay. Length of this. Okay, so let me just look at the structure that we have here, because I want to get this. Okay, so we've got that. I see, comma 1, comma, and then this rule. All right, what we want to do is arrow that rule, and then we want to do that interactive list selector on that. Does that make sense? Okay, so we've got this, we've got gather by, and this is the first thing, the length of the thing. Okay, let's do this. Arrow that, and then let us say interactive list selector. Okay, of this, and then do we want to, so what we're doing here is this time-constrained canonical graph, which is not the most fantastic thing to try to do, but I guess it's okay. And by the time we fix the code, we might as well have had it run. Okay, so now we're going to do this case. Now, Ed, is there something obvious about some of these rules? Some of these rules are not even non-deterministic, right?
Right. Some of them are rather boring.
Well, no. But you understand, if I look at this, right? If I look at this thing where I've got all these rules, some of these rules don't have any duplicates in their left-hand sides.
Correct.
Do you understand what I'm saying? So they're not non-deterministic. So we already studied them as deterministic Turing machines. Now,
Right.
interestingly, those deterministic Turing machines will halt at some point. They'll simply stop their evolution, which I believe the Turing machine function does correctly, doesn't it? Mano, do you know?
No, I don't.
Well, maybe we can determine that. Okay, let's take. Okay, hold on a second. Let's do 3 cases in rule, and let's distinguish the case. This is 3 cases here, and let's look at. Let's see. What's the test for deterministic? The test for deterministic is that the left-hand sides of each of these. Okay, so test deterministic of a rule. That's a rule list, actually. And what we're doing then is we might as well flatten the rule list. It's not going to do us any harm to do that. Then we want to say first / at left-hand side. And then is there a duplicates? Is there a thing that just tests whether there are duplicates? You don't know. Okay.
I usually do union.
I understand. We can do that. I mean, but so then we say hash triple equals, I know, length of hash triple equals length of union of hash, right? Apply that to this, correct?
Mhm.
Okay, so now let's say select in there test deterministic. Okay, so the length of that. So that's 2048 of those guys are deterministic, which is probably obvious because that's choosing, Ed, what's the combinatorics of this? We've got 4 cases to choose from, and we're choosing 3 of those cases, right? Without duplication.
2 to the 8th? 2 to the 4th or something?
No. No, because you've got, oh, I see what you're saying. You're picking, all right, I believe you to some extent. Okay, so then here, to get the non-deterministic ones, we would say, I never remember how to do these. Is it not at star this? I think so. Okay, so then there are 2912 of those. Is that a little odd? What's the total number? The total number is binomial coefficient of how many subsets of these are there? How many length 3 subsets? Do you understand my question?
It'll be something choose 3. How
Oh.
many?
I think we'd worked that out up at the top here. Binomial 32, choose 3. Okay. So this is binomial 32, choose 3 is 2960. And 2960, I can't do my arithmetic correctly, 2048. Great. Great. Okay, that's fine. All right, so these are the ones that have non-determinism in them. These are the ones that don't have non-determinism, right?
Mm-hmm.
So, okay, so down here, there's not a lot of point in us studying the case where it doesn't have non-determinism. So what I should go ahead and do here is say select actually, I just want to check one thing. Test deterministic. I want to check one thing here. I want to check that if we look at the multiway graphs for these ones which we think are deterministic, that they are all in fact trivial. You see what I'm saying?
Uh-huh.
So it should be the case here. Let's do this computation. On that. And now let's say select in there. These should run really pretty fast, and there might be only one case here because we're selecting based on the multiway graph. Okay. That's mildly confusing to me. Oh no, it isn't. Well, oh, I see. These are ones that, no, I'm very confused here. How can this, if it has a deterministic left-hand side, why does it show something which has multiple possible head positions here? Do you understand what I'm asking?
Yeah.
Seems wrong to me. I mean, these
Yeah, it
multi-way
does.
graphs don't look wrong. These multi-way graphs, that's a case where it's just looping. Okay.
Do a add on the counts and see if it gets the right number.
These counts here,
Yeah, uh-huh.
I'm sure they're going to be right. But never hurts to check, I guess. All accounted for. All present and accounted for. Okay, so the question...
You've got the wrong count there. It should be the other number.
No,
These are the deterministic ones, not the non...
That's the deterministic ones. I did exactly the right thing. I tested here. This is the select for the deterministic. There's 2048 of those. It's right.
Okay.
Okay, but this is confusing. That doesn't look right. Okay, so let's take a look at this rule here. That's just a sample of all those rules. And by the way, they don't all need to produce the same picture here because I'm only selecting on the left-hand side here. Do you get what I'm saying?
Yeah.
Okay, but let's take this one as an example. Do I have to say this for rule plot? Is that right? No, I don't say that for rule plot. That's a mistake, but I don't, right? Is that correct, Mano? No? What do I do
No, you do
here?
say it.
Okay, I do say it for rule plot, but I don't say it for one of these others. Okay, fine. So that's a deterministic rule.
Mm-hmm.
How can this head wind up in different positions here? Okay, let's see what we're actually doing here. So we're saying let's see, we've got a multi-way Turing machine here with that rule. Okay, so this I'm officially confused here. Okay, this is very, very confusing. You see that? This is not giving. What is happening here? Do you understand my confusion? This rule is deterministic.
But
Right?
the evolution is non-deterministic.
Yeah, how can it end up with different evolutions here? Unless there's a bug in multi-way Turing machine. Okay, so let's take a look at this more carefully. Okay, so let's just look at the first step, 160 here. It's a bunch of zeros, and it's in state 1. And it's this case, right? That's state 1 there, I think. Okay, it moves to the left. Wait a minute. How can it do this? That's the Turing machine doing nothing. That's incorrect. It shouldn't be able to do nothing. Do you understand what I'm saying?
Yeah.
I think that's a bug in multi-way Turing machine. Oh dear.
I'll note this down.
Well,
And talk.
no, we just blew up our whole project here right now. If that's wrong, then everything we've done with multi-way Turing machine is wrong.
Unless it's a special bug for blank tapes.
It's not a special bug for blank tapes. It's a special bug because this is somehow using the Turing machine function or something. No, it's somehow keeping the state. Okay, look, the 160 state is being kept all the way through. Do you understand what I'm saying?
Yeah.
Now, that's also confusing with respect to this, because this is not showing that state being kept, right? Because this would branch in this case, but it's not branching. Do you understand what I'm saying?
Sorry, say that one more time.
Okay, look, see this multi-way graph, okay?
Mhm.
And see this here. This says one state here is branching into two states. But that's
Yeah.
not what this multi-way graph shows.
Mm-hmm.
What is the thing that generates this from a multi-way evolution? Is this states list? I mean, I'm using the default here, but maybe I have to use states list explicitly. Let's look. Oh, for goodness sake. What is it called? Did you understand what I'm asking?
All states list?
Same bug. Well, I think that's what we have to track down. Maybe we should move to a different topic here because this is just blown up. Well, I'm glad we checked this. Yeah, this is basically giving us the wrong result for every non-deterministic Turing machine here.
I let Jonathan know about it.
I hope this doesn't affect the things that I did with rule Turing machines. No, it won't do because they don't have this issue. They have all possible, they're all possible configurations, all possible transitions are allowed there. So that won't happen. Right. Yeah, well, this is all wrong. Weird. Do you want to take here? I can just give you this. This is the minimal case. I'll just send it to you here.
Yeah. Is there any reason that you know, the non-deterministic rule evolutions shouldn't work though?
Non-deterministic rule evolutions. What do you mean by that?
Is there
Well,
any
yeah,
reason
because it's putting down a result that shouldn't be there.
right?
Okay, so it's going to randomize all the results,
Mm-hmm.
right? Because it's leaving a state that shouldn't be left. I mean, conceivably, wait a minute. Maybe we have to complement successive steps, but it shouldn't be necessary. Do you understand what I'm saying? To say, if we complement successive steps here, right? Form successive complements. But I think that's not right. I mean, we're going to end up here with a whole accumulation of incorrect states. Right? It shouldn't be adding the no change state. It's got an effective rule. It's got an effective no change rule that's adding to everything else. Make sense?
Yeah.
Okay, so I'm gonna put something in here. I'm gonna write something right now, just so that we can do something here. We're going to call it hacked. Hacked TM evolution. MWTM evolution. Hacked MWTM. And it's got a rule, and it's got an init, and it's got a number of steps. Okay. And the hacked version of this is this. Let's see, we want to do a fold. Who can figure out how to do this? Each successive one wants to be the complement. Do you understand what we're doing? We're complementing successive things. So this one wants to complement back the previous one. Right? I think this is a fold. What do you think? It's a fold of complement of hash. Is it complement hash 2? Let's see. Who can figure this out? Ed, can you figure this out? Do you understand what I'm talking about here?
I think so.
Well, what do you think the right answer is?
I do like the idea with complement.
No. I'm asking about fold list. Do you understand? I'm asking, is this code correct? That's what I'm asking.
That looks good to me.
Really?
Yeah, I think so.
I'm going to be surprised if it works. Well, surprises never cease. Okay, hacked MWTM. Okay, so let's run that in here. Instead of this, we want, instead of that whole thing, hacked MWTM. Move that. Let's see what this does. So this should show representative deterministic evolutions. Oh, for goodness freaking. Oh, no, actually, this is not necessarily wrong. No, actually, this isn't wrong. This is right. You see that? There's only one. No. What happened here? There are two head positions on the same step.
Yeah.
See what I'm saying?
Mm-hmm.
Okay, let's look at this one here. Oh, no. It's wrong. It's just wrong, right? It didn't do it correctly. This thing didn't work correctly. Okay, let's look at this. 1, 1. Okay, so up to there, it removed it correctly. But by this point,
To take the complement of every list that comes before it, not just the previous one.
you're right. Okay, how do we do that? What we want is a generalization of fold list, which I think we have. Is it sequence fold list? Well, it may be easier to just write this explicitly. So what do we want to do? We want to say, we want to fold the thing in where at every step we have two things. We're accumulating two things, okay? What we're accumulating is the join or the union of hash 1, of list hash 1 with, no, I'm sorry, of hash 1 with list hash 2, if I'm not mistaken. Is that right? We have the union, and then we're going to have, do you understand what I'm doing? No. Okay. So look here. Okay. Let me go through it. Okay. So what I'm going to accumulate at each point, I'm going to have, that's the cumulative complement list. Okay.
Mm-hmm.
Right. The first thing is the cumulative complement list. So I'm going to get the new cumulative complement list. And then the second thing is going to be the complement with first of hash of hash 2. Okay. And then the thing here should be is the union well, actually, the easiest thing to do is just to fold the union into the whole thing. Just to fold list a union and then complement against each one. Is that right?
Another way to do it might be to use our original technique, but go through the list in reverse.
Why is that going to work?
Because at each step, you're left with the only new item, right?
I'm confused by that comment. I mean, we can try it, but so what are you saying? So you're saying fold list complement of what? Hash of the thing you've got so far. I don't understand this. I don't understand what you're suggesting here. What do you think the code should be?
What was the original function?
This one here.
Yeah, so we would just do it over the reversed evolution.
Wait. This didn't work at all. This didn't work at all. Oh, that's because I added this stuff here. Okay, what are you saying? So what are you suggesting?
We would have to do it over the reversed evolution, no? Because at the end you end up with all the accumulated states, right? And then comparing to the step before that, you're left with only the new final state, and then
Oh, so we can reverse this. That's fine. Okay, now what are you claiming here? No, this is nonsense.
Okay, sorry.
Okay, can we go through what we actually need to do here? Okay, so what we're trying to do is at every step, we want the union of everything that's come before. So what we want is the accumulated union. So what we can do there is we can say, okay, so let's do this. There's our result. By the way, I hope we didn't do this. We didn't get this wrong, did we? And put a fixed rule. Hold on. Yeah, this is obviously wrong. That's not a fixed rule. That should just say rule there. Was a nasty problem. Okay, so but that was not, that doesn't explain the issue that we had. Okay. So with A equals that, now what we want to do is we want to say fold list union, comma A, and that gives us the set of union things. And so for each one of these, we want to say into this thing A, we want to complement it with everything to the left of what it is, you know, to one step to the left in this list. Does that make sense?
Yeah.
Now that list, how long is that list? That fold list is one shorter than the original list, I believe. Do you understand what I'm saying? Okay, so this list here, length 6. Okay, I'm confused by that. I don't understand why it's length 6. And each one of those okay, will be one longer. Making sense? And then here, what we need to do is take each result and complement it with the thing one to its left. Do you understand what I'm saying?
Mm-hmm.
Right? So I'm confused by this. I'm very confused because this first one, we don't want this first one. We want the rest of this list because this first one is not to be complemented with anything. That one wait a minute. I think what we do now is we do exactly this complement thing that we did before. I think. Let's see if I'm right about that. What? I don't understand.
One possible method would be to
No. We were making another mistake. We're making another mistake. I think these things that have one too many list brackets or something. We got to understand what actually happened here, okay? Why did that get two things there? So that first one complemented correctly. You see here, okay, so that makes the union of each thing up to that stage. Then we want to complement with the thing. Oh, I see what's wrong here. What we want to do is say partition, comma 2, comma 1. And then we want to say I think, is this right? And we want to say, is this right? More promising indeed. Do you understand what that did? Total mystification. Okay, so here we're going to do the hacked. Oh, great. Well, something's gone horribly wrong here. That could be because this thing will actually give 0. Right, that will give a null list. The problem with that is it's going to give a null list there. Do you see what I'm saying? If the thing
Yeah.
halts, it will give a null list, I think.
Mhm.
It'd be handy if for parallel mapping for error handling to be done differently.
Thank you. That's the least of our problem. I mean, parallel stuff is, by the time you're doing it across multiple machines, it's a pretty complicated story. Okay, so let's try this again. Okay, so basically, I want to note early non-MW results are wrong. Oh, this is frustrating. Okay, let's go back down here. Can we pay attention, try and understand why this code is wrong? What on earth is it doing there? Okay. Oh, we got to reevaluate rule cases here. Okay. Hacked MWTM. Okay, so this show multiway, where's that result here? The multiway graphics stuff. Where's the test deterministic? That's another. Okay, how are we going to do this? I think what we're getting is, do you understand the issue here? Do you understand what happened? I have no idea. I think there's a chance that if we just say delete cases in there of null list, that we might solve this. Let's just try it. I mean, this is kind of stupid because the chance of this working is not that high, but let's just try this. Do you understand what that's doing? That's dealing with the case where the Turing machine halted and then it just put in a null list from the complements.
Oh, that makes sense.
And then the multi-way Turing graphics got totally confused.
Why is the number of kernels a lot smaller?
It's 93.
Doesn't the union thing also remove, states that repeat after some time?
Possibly, yes. Okay, this is much more promising, despite that weirdness there. This looks correct. Okay, I mean, it's not the best presentation, and we probably want to improve the presentation. What on earth is that? Let me rerun this just in case we had some glitch from having a race condition on the parallel kernel initialization. Yeah, better. Okay, I think that's looking roughly correct. So in other words, that's what happens. That's a typical, that won't be the only one, but because that's just a sample of what it does in the case where it doesn't halt. You get what I'm saying?
Yeah.
Okay, terrific. So now, let us do the non-deterministic case. Okay, 2912 cases. Let's see what they do. So it's interesting. So this is the time to halt for these different deterministic Turing machines with incomplete, specifications. If you understand what I'm saying. Oh dear, what's that doing? Okay, here we go. Okay, these look much more reasonable. Okay, so there it's just couldn't decide which side to go on. Brilliant. Okay, this looks really good. This looks right, finally. Okay. So that one looks a little bit complicated, not incredibly so, but a little bit complicated. So many of these, yeah, this is looking sensible. I mean, again, something like that has multiple. Let's pick that one up and take a look at that one just for the hell of it. It's the most interesting one. That one looks rather jolly down there. Let's take a look at that guy.
Yeah, that one looks more interesting.
Okay. Okay. And let's now go ahead. This stuff we did here is probably wrong, because what we really want to do here, up here, yeah, this stuff is all wrong, because this wants to be, instead of this, it wants to be a hack TM thing, right? So this one here, that wants to say hacked MWTM, and then I want to get rid of okay. So these up here, this is probably wrong. And so is this. Although I think this Monte Carlo approach is not going to work anyway. So, okay, but those are probably wrong. So then here, what we want to do, again, instead of this, we want to say hacked MWTM. Okay, instead of this, hacked MWTM. It wasn't very different. It just didn't have as much stuff going on there. So let's say up to size 14 or something. Okay, so that's interesting. So that's kind of what we would expect. This was quadratic because it was accumulating all the things that it shouldn't, you know, all the previous values as well. Makes
Right.
sense? So this one here wants to be hacked MWTM also. Oh, that's much jollier. I see. Okay. So let's see. So we want to take this stuff here and use it for that other Turing machine function. Down here. This is really a kind of a cruddy way to do it, but it'll work. Okay. It's not that exciting, but we can try it anyway. That's irrelevant. Oh, that's rather jolly. Okay, let's try that with like 15 steps. Okay, that's interesting. So that's probably what we're seeing there is well, we probably see it from the rule. Can you see what's happening from the rule? Oh, wow, look at that. So that's kind of, I mean, that's kind of what we saw here, except this thing is a flip around of that. Let's see what it does for the head. Okay, so the head position, it's ending up writing further away there. All right, let's try the real thing we want to try, which is the first case where we actually think we can get something non-trivial. Okay, so let's do this case here. Let's first of all do the deterministic case. We should have 4096 of those. And let's see how long they take to halt. I think this is, I think these will be trivially, right? If we do rule cases 4 and we say test deterministic, I think there will be 4096 of these. Yep, okay. And I think this will show us the standard sort of pattern of deterministic Turing machine behavior. And then I'm going to, okay.
I believe you.
Right, so most of them, so it's actually interesting that some of them halt, because it's not obvious that any would halt. You see what I'm saying?
But we're removing repeated states, right? So there are some that actually cycle, but you can't see that from this.
I guess that's correct, yes. So that's what's happening. Those are the ones that go to a fixed condition, right? Okay. Okay, let's go more ambitious here. Okay, let's look at the non-deterministic case here. This was what we really wanted to do from the beginning. $31,000 of these creatures. Let's make it wider so we can have more space to look at it. Oh, I'm going to stop this if I can. I realized I want to set it up for that interactive whatever thing. Oh, drat. Well, let me kill this off, and I'm going to set it up slightly differently because I want to Okay, let's collect all the things we needed for this. We needed that hacked, whatever it was. Where is it? Hacked MWTM. And we also had test deterministic. And then these want to be combined with the stuff at the top here. And we also need to run your code over here. And we need to run this. Okay. And now down here, I want to say
Need rule cases as well.
yes, okay, hold on. Okay, are we ready? Oh, we got to launch all these kernels again. Questions on our live stream. Parmenides is asking, will the CEO live streams be coming back soon? I hope so. We are in the middle of our winter school for physics project. And so I have a bunch of meetings related to that, but I think we have some live streams coming up in the next few days. All right, let's see how this is going to do. This is going a little slowly. Yeah, and ask for a Q&A. Yeah, I should do another Q&A about the physics project. I think we're kind of ready for that. Yes, it's a good thing to do. I'd like to do that. And we're also doing a science Q&A. Yes, that will be on. We're doing 2 this week. One is I'm doing one about business and innovation. That's a new series on Thursday, and our regular science and technology Q&A for kids and others on Friday, which I could have done last week, but nobody else was available to help with that, so we didn't do it. But that will be coming back this week. Okay, come on, run, computer. Okay, I want to just look ahead for a few things I want to do. So in addition to, we're doing non-deterministic Turing machines. There are these other cases of non-determinism that I would really like to look at. Tilings, aggregation systems, these kinds of things. And I think, Ed, you had sent me some stuff about tilings. I also want to take a quick look at tag systems if we have a chance. So let's wait for this to come back and see whether anything exciting happens here. I mean, reminding ourselves what we expect here. We expect there's going to be the simplest universal non-deterministic Turing machine will be hiding in this collection. So our mission is to identify it. And gosh, it's just running. I don't know why is it going slower than it went before? Okay, it's predicting completion in like 14 minutes, so we should be doing something different while this is running. Let's just review what we expect to see, okay? We're going to see a bunch of multi-way graphs, some of which will be somewhat complicated, many of which will look very simple. And what we're trying to identify is potential Turing machines that okay, so what are we looking for? We're looking for something where essentially the machine is capable of, let's say, factoring integers, where what we are asking for is that one of the branches in the multiway graph has the answer. That's what we define as kind of success in an NP style problem, so to speak, right, guys?
Mm-hmm.
And so the question is, with one of these Turing machines, is it possible to encode, to set it up so that at least one branch here can do an arbitrary computation? Now, we know if we were doing just one branch, in other words, if there was only one branch at all, we know we need to go to a 2-3 Turing machine before we get universality. But given that we are allowed to pick the branch, we expect that we could have a simpler Turing machine. So in other words, the sort of the test here is if we were to look down if we were to look down every branch, right, what this is saying is there exist branches which show complicated behavior, basically, that while any given branch, right, so case of interest, there exists a branch with quotes complicated behavior. So in other words, there is a path through the multiway graph. But now, one thing that's very funky about that is, what if we pick the path specially to get complicated behavior? How much picking of the path can we do? Right, and that's similar to the question of I mean, if we are using a quantum computer and we're trying to figure out what was the answer, measurement is essentially a path picking or a path combining operation. And so the question is, how much computation are we putting into that effort? In other words, if we say that, to find complicated behavior, we're allowed to do this whole elaborate thing where we pick, where we have many branches in the multiway graph, and at every branch we're carefully picking which one we want to get. Like, let's say, for example, we had all possible paths, and our picking function is picking some complicated, very hard to compute sequence of zeros and ones. That would not be considered, that wasn't, the Turing machine isn't doing the heavy lifting then. Something else is doing the heavy lifting. So a question would be, what criteria can we use? Yeah, it's interesting. I mean, so in the normal formulation of like an NP problem, the whole point is the checking function is polynomial time.
I'm going to make a conjecture that you'll find the most interesting behavior with slight modifications to counters.
Maybe. Yeah, I mean, counters grow slowly. That's not what I don't know. I mean, that universal Turing machine that I found and then Alex Smith proved back 20 years ago or something is I don't know how close that is to a counter. Good question. I mean, anyway, we're about to come on. We're going to get a result here, hopefully. What is its ETA? Oh, come on, 3 more minutes. Well, anyway, once we've done this, I would like to look at, so you had started looking at something with tilings, right, Ed?
Yes. It's pretty fast, but so far hasn't found anything. I've got a large block of forbidden subsets because we know that those lead to repetitive behavior. And I've also got code for whether a given set of tiles can be valid. And so far, out of many searches, I haven't found anything that passes both tests.
Well, wait a second. So we know in the case of the 5-tuple thing that, I mean, we know how that works, right? So you should be able to validate your thing based on the 5-tuple case. If you can get the 5-tuple case quickly, I'll be impressed. So just to remind you what we were doing there, I mean, this is from 30 years ago now, and where computers were a lot slower.
Right.
this
Yours
case-
is slightly different though, is because your 5-tuple uses a seed case.
No,
And it's-
no. Ed, no, not in this case here. These are not seeded.
I see.
Okay, so this is what this is. The first thing here is, given these 5 tuples, what are the minimal cases that allow tiling? Do you understand what I'm saying?
Right.
So in other words, if you were to remove one of these allowed things, this probably wouldn't tile at all.
Right.
Right? Okay, so at the first moment of tiling,
Right. If you open up forbidden subsets in the next notebook, you'll see, and scroll down so you can see them. Those are the subsets that do tilings that are repetitive. So we want to forbid those.
Wait. So are you telling me that those are the only subsets that do tilings?
Oh no, these are the only ones that only have up to 5 tiles in their set that do tilings.
I see. So to validate what you're doing, could you do the case of these 5 tuples here, just so we know we're getting the same answer?
Sure. And if you can take a look at if you open up the next cell, you can see the ones that are for 6. And no, the right above that. I've got a closed cell. Those are the length 6.
Oh yeah, wonderful.
Sets.
Well done. Well, that's okay. Things are getting better. I mean, because this took quite a lot of effort 30 years ago. Okay. Oh, look, we're getting some results back. Let's see if this. Let's just hope this doesn't go up. We got results. Okay, let's take a little look here.
Hit save.
All right. Okay. So what we're going to do here is we're going to be selecting which ones look like they have a chance of being interesting. And I'm still a little bit confused. I'm just not used to non-deterministic computation here. So I'm not used to this question of, of does there exist a path and how that all works. Oh boy, there's a lot of these creatures, a lot of distinct creatures here. So
we should have sorted by the last value.
Doesn't matter. Oh my gosh. All right, story of my life, going through these kinds of weird things. Okay, so let's take a look here. So a lot of these are very tree-y, and they don't seem to be doing anything. They don't seem to have a lot of choice here. So a lot of, I mean, they seem to have sort of be following all possible paths. So let's just take a quick look through here. And let me know if you see something interesting. All right, so I think we looked at these a little bit before, these ones here.
3 up from the bottom on the third one.
Here?
Down a little bit.
This guy?
Yeah. And one nearby has a large cycle in it. Is night move down.
This one here?
No, the other way.
This thing.
That one, yeah.
Yeah, that's interesting. I agree. That one is interesting. Although I think that's just an early cycle, so to speak. I don't think that's going to be a surviving cycle, if you understand what I'm saying.
Right. It'd be good if we started adding numbers to the add values. And that way I could just give you a number rather than guide you around.
Well, that's a good point. I mean, we just enumerate. Yeah, okay, good suggestion for the next time. I'm not used to doing these with just more than just on my own. Okay, that's a curious one. I rather like that one. That one's interesting. Because that one seems to be deterministic in terms of the I mean, most of these are just spraying out different cases. Okay. That one is just interesting as an example of something different.
The next two down, I guess everything else dies except for single cases.
These ones here. This one here, for
Yes.
example. See, I don't understand that looking at this picture.
I don't think it's interesting, but it looks like it dies.
Well, right. Look, the thing I'm still trying to understand is how do we characterize the analog of the sort of search for complex behavior in a deterministic system? What is its analog in a non-deterministic system? I don't yet understand.
The enumeration will also help on Rocket Chat.
Yeah, okay, well, remind me to do that next time. Okay, so pick some others you think look interesting. I don't think these are. I think this is not going to be interesting.
We need some sort of sort mechanism on the shape as well.
Well, we can pull them in and use machine learning and try and classify them. It's not a crazy thing to do. I want to look at one of these. See, I just don't get how to identify. I mean, one possibility is that the multiway system is itself complicated. I also would like to look at the causal graphs for some of these. I'm still very confused by if you are, if you have a deterministic Turing machine and you live in a universe where the whole universe is governed by a deterministic Turing machine, then it's pretty easy to see that the only thing you are ultimately sensitive to is the causal graph. Go ahead. What?
The one at the very bottom, bottom left.
This one here?
I don't see what's going on with that one.
I think it's basically deterministic, but we'll pick it out and take a look. See, these are not encouraging. I mean, even though their multiway graph looks complicated, it's not encouraging in terms of what the actual behavior is. Humph. I wonder what that one does. I think that's similar to one we looked at before. I mean, remember, we're only going 5 steps here, so we don't get to see very much. And arguably, we should be just pruning these based on, stopping with a certain maximum size of multiway graph.
Right.
I don't know what these are doing.
The one in the center there is very power of 2 oriented.
Which one? This one here?
Center, go up 2. Go up 2. That one is powers of 2 for some reason.
Well, it's just allowing all possibilities, I think. But it's a little bit surprising that it looks like it's a deterministic evolution over here. That's a bit surprising.
And 2 over, it's same thing, but
2 over from what? From the previous one?
Right. Slightly different, but
Minor
same graph.
Yeah. Oh boy, in another century, I would have been some kind of animal zoology specimen collector. I don't know whether this is easier or harder than, going into some rainforest and shaking a tree and seeing what falls out.
At least these don't bite.
Yeah, I think that's been said before, right? That's
I was recently researching the main characters and building the fossil record, and they were true enemies.
is that surprising? Were they academics? Those are always good sources of.
Yeah,
Okay.
there's a big feud between the fossil collectors that lasted 30 years.
Well, there's more fossils to. It's okay. There's more fossils to dig up. Just go pick your Montana or wherever it is, and okay, what else are we seeing here? There's quite a lot of diversity in these. Okay, there we go. All right, let's copy these. All right, let's go ahead and use that same code. If only I can get there. I mean, I wonder whether we want to look at. No, it's okay. Was this the code that we used for that? Oh, this is going to be close enough. Okay. Okay, so let's take these, this list, instead of this, instead of any of this. And then let's go ahead here. Let's just go to at least to t equals 6, even if that's not that exciting. Okay. All right, let's see whether we can extend that. Most of these look like they're not going to blow themselves up. So let's see if we can extend that to t equals 9, for example. Maybe we should put in a time constraint here.
No, it'll work.
Okay. So let's take this guy, for example. I don't quite understand why that's only 9 steps there. Okay, so this one. Oh, boy. This is complicated. Wow. Okay, what about this one here? Boy, I wish we had that working with okay, what do we think this one is doing? I mean, what we have to do is to look at what the actual states are here. That makes sense?
Mm-hmm.
Even if we could get an indication of like the head position for each of these, that would give us a sort of a hash code for the state.
Oh, take a look at the one in the middle that looks like kind of a line. You've got a pyramid similar to the one.
Which one? Which one that looks like a line? This one here.
That one, yeah. The graph has something of the same structure of the one we found interesting before.
Yeah, but I think I'm confused by the interpretation of these things because, if you look at this for deterministic Turing machines, what you find is a whole range of behavior. And sometimes that behavior is complex, but the question is, in this case, again, we're reviewing what it means to, there are many possible paths here. The aggregate of all the paths, it's this question, does there exist a path that has complicated behavior, or what is the criterion here? You understand the question?
Yeah, I think so.
So what's the analog of a search for complex behavior starting from a simple initial condition? And what we're seeing, in a case like this, let's look at this one, just for the hell of it. Let's look at that one a little bit more closely. So let's say Turing machine plot. I'm now forgetting, is this one we have to do the flatten to get the thing, 2-2 rule plot? Is that right?
Mm-hmm.
I know.
Yeah.
Okay, do you have any fix for that thing with the states graph? Do we know how to fix that?
No, not yet.
Can we just use a state rendering function?
Let's see.
All right, so anyway, what this is saying is, so first of all, this never involves the second color. That makes me think of something. I don't think we looked at this. We started looking at this last time. Case of k equals 1, the one color case. Am I making sense? We haven't looked at this for the one color case. And if we go back all the way up here and we say, this rule case is we want S12, C00, C100, rule case is 1. That should be a smaller set. And then we could just look at the following thing. Yeah. Let's go here. Actually, we want to go slightly further down here. Okay. Okay, so this is rule case is 1. And let's just to be systematic, so this is the non-deterministic case, and maybe there's nothing there. Okay, those are trivial. So that's the case with k equals 1, 2 cases in the rule, non-deterministic. K equals 1, 3 cases in the rule. Okay, so it's interesting that we already get some of these kinds of things. And let's be a little bit more dangerous about it. Let's go up to 7, for example, here. Maybe even we can go to 10, because I think it's not going to, I don't think you can get exponentially many cases. All right, so now let's go to 4 cases in the rule. I don't think we're seeing anything different. Now notice that one of the things we're not doing here, subsets will have at most one of anything in that thing, right? Am I making sense? There'll be at most one of each particular rule case. So if we say length of rule case is 1, there are 8. Okay, so we can have up to 8. This number 4 could go all the way up to 8.
Mm-hmm.
So these are the non-deterministic rules. So let's go ahead and look at them all. See whether anything happens. Okay, so it's getting less interesting, probably because we're using, well, I'm not sure, but let's just see here. So 6. Is it obvious why these are getting less interesting? Maybe they're just fewer case possible rules. Because at 8, there should only be one. There should be no non-deterministic ones at 8. I'm actually confused why there's even one at 8. Oh, I see. Yes, there's one where this is the maximally non-deterministic case. This is essentially, this is the Rulial limit of complete non-determinism. You see what I'm saying? Where every possible final state can occur. Right? And down up here, we've got many fewer states can occur, many fewer cases can occur. Makes sense to people?
Uh-huh.
So, I mean, this is kind of the most interesting thing that seems to happen in this case. But notice that it already happens. We already discovered it happening in this case here, right? But I don't yet understand what it's doing. Now, just for completeness, let's look at the deterministic cases here with k equals 1, which I predict will be pretty boring. All right, let's look at one case. Nothing. Boring. Oh, sorry, that was the non-deterministic. Let's take test deterministic. Okay, that's one case in the rule where basically it's just saying this is what the 0 state does. Okay.
Mm-hmm.
Okay. So I don't think anything much is going to happen here. And by the time we're above 4 rather, okay, there were no cases there. Now, why isn't this one going to give something? Why does that not give? Let's see. That should be giving, there should be a rule. I don't understand that. Oh, there are only 2 cases. Right. It's always blank and the head is either up or down. So below 3 cases, there's no possibility of anything. Yeah, you can't get a deterministic rule above 2 cases.
Right. Only 2 unique left-hand sides.
Yes. So, okay, I am still so confused. I mean, let's look at this one for a moment more. Wait a minute, did we pick that one up? Let me pick that one up, copy. This was this case, and now we had looked up above here at okay, that's that case. All right, so now we want to look at, so this one, again, let's review what this does. The multiway graph for this guy is okay, do you understand this? Wait a minute. So this has gone, this has become deterministic down here. Right? So
Yeah.
let's,
That or the rest is more complicated.
what do you mean?
It could be that one case is going off on its. Oh, actually, I guess it is deterministic. Everything is leading.
No, this is more complicated because look what's happened. At 15 steps, kind of there's a direct way to get to the end, and then there's this indirect way to get to the end. So, oh boy, how do we want to look at this? We could just enumerate paths through here and look at what the deterministic evolution is for every enumerated path through this thing. Because at each step, okay, so let's look at it for the case of 5. I'm actually rather confused by why this tail.
Oh, it's basically there's only one case that gets to the last dot, and there's twice as many that get to the dot before, and so on. Basically, as soon as you do the wrong thing, you're forced into that thing that terminates. And there's only a few cases that stick around on the left that haven't done the bad thing yet. It's like being in a room with
Okay.
a button, and if you press it, it blows up. And you basically want to stay in the room without pressing the button.
Okay, well, let's look then. Okay, so here, if we were to look at this, okay, I don't really understand this. So this is saying, okay, I don't really understand. But maybe what we should do is look at the actual states that you can get to. Right, at every step, how many states are there that you can get to? So let's go ahead and look at, okay, so here, if we just get this, the heck, oh. Okay, how many states are there at each step here? I think there's just 2. Oh no, there aren't. Weird. Okay, so what are these states? So we can plot. Mano, does your TM graphics do a single line graphic for these? Do you understand my question?
Yeah, it does. I think you can use evolution plot.
You mean in Turing machine plot?
Yeah.
Okay. So if I map, see, look at this. Well, first of all, we don't have to worry about the tape. This is just a position of the head story, right? And what this is doing is at every step, let's just collect up the positions of the heads. Okay? Actually, we might want the head and the state because it may be the way it's going. Okay, so let's look here. And let's say map take hash comma 2. No, hash sub 1 comma 2. That thing at level 2. Okay, so those are the positions of the heads and the states at each of these different steps. Let's just run this a while longer to see what it does. Okay, so what we have here, apart from that one glitch at the beginning, at each step, we have 3 possibilities. So it looks like it's just, right? It's just 1 and 2. It's basically this side is 2/3 the weight, and this is 1/3 the weight. And that's what it's doing. So it's either going, and by the time it's on this side, I see. So on this side, there are 2 possibilities because it's flipping around between state 1 and state 2. Making sense?
Yes.
But on this side, it can only go this way. So let's look at what that looks like in the multiway system. Gosh, it's kind of weird. Do you understand what it's doing here? Well, let's see what happens if I say for this. Oh, it is a layered graph plot. Okay, so I think we need to label these by the state, by this information for every one of these. So Mano, how do we do that? That's a state rendering function, right? In the multiway Turing machine thing. Yes?
Yeah.
Okay,
I'm
so
just worried it's going to be broken again, but
state rendering function. What does state rendering function get given? What is its argument? Can you look it up?
yeah, looking. You can do inherited. Uses
No,
the
no,
explicit
no.
vertex.
I don't want that. I want to compute something from here. That's the whole point. Do you understand what I'm saying? I mean, I want to compute. Okay, so what is it supposed to return? What is state rendering function supposed to return? What does it take as an argument, or what does it return?
It can take a function as an argument.
No, I understand. It's value. What does the function given? What are the arguments of the function? What is given to the state rendering function, and what is it supposed to return?
Sorry, I have to look a bit more closely. Doesn't look like there are examples for this in the documentation.
Well, look it up for another multiway system. Look it up for the main multiway system.
Yeah, it still doesn't have an example of it, but let me check the source code.
It should have an example of it. Oh, gosh. Well, that's a bug. My gosh, look at all these cases. Okay, state rendering function. Okay, apply this to the name of the vertex. Yeah, we just don't know what it's supposed to return. Well, let's just see what happens if I say text of that. That wasn't very useful. I think it's got to return something with a position, but how does it get given the potential positions? Do you understand what I'm asking?
Yeah. I think it does have to get a position. I'm looking through the function now.
Okay. Well, I've used this function, so I can look up what I did. Let's see, what was a case where this was done? In the combinator case, there are definitely places where I use this. Let's take a look here. You know, this needs a table of contents. Okay, this definitely has one of these. Oh, don't tell me it has a cloud get thing in it. How do you get the actual code from this, Mano?
I'm not sure, but it should be in the like Code 04 notebook that we were using.
You know what? I've got a better solution. Well, this is fairly grotesque. This is really grotesque. Why am I seeing this? This is not right. This is not what we should be getting here. Anyway, okay, let's look for state rendering function. How can there be no state rendering function in here? Because I did it myself is the answer. Because I didn't trust this and I just wrote it myself. Oh boy. Okay. All right. Look, we okay. So that maybe we should do this offline. We've got to fix this thing so that it actually displays. So we can either display just in this case. I think one of these is going to be so the branches here. I'm just really confused by the fact that this converges back to this again. That's what I'm really confused by. I mean, if we look at this picture, it seems like it's made a decision. It's either going to the left or it's going to the right, and it can't get back again. And if we look at the actual rule, I see. In state 1, it can go either way, right? In state 2, it can only go to the right. Am I making sense?
Yes. Yes.
But I don't understand why there's no intermediate case here. Right? This is a bunch of state 2s that all go to the right.
Yeah, once it hits state 2, it's always going to go to the right.
I understand, but from this state here, which is state 1, why is there not this case then? Why is there not something where it's streaming off to the right from here? Do you get what I'm saying?
Okay, this thought isn't fully formed, but might it be because we're deleting repeated states and it could resemble
That's I was
like,
going to say the same thing.
All right.
yeah, if
so,
you can verbalize
Mano, I I leave it to you to untangle this, okay, and get it right, because the original thing is this bug in multi-way Turing machine that's causing it to replicate the unchanged state.
Yeah.
Right.
Okay.
So if you can start off and try and understand why that went wrong, then I think we'll have to, we'll see what that means. Although the big question for me is the interpretation of this non-deterministic computation, what that means. Look, I was going to look at a couple of other systems where we can make a multi-way graph out of them. So, let me just for the sake of
for reference, I tossed the binary counter into the chat.
What?
For reference, I tossed the binary counter into the chat.
Yeah, unfortunately, if you're expecting me to be able to see Zoom chat, I can't because of a bug.
It's a machine 378.
I'm passing it to Rocket Chat.
Okay. Why are you showing me this?
I think that's the best Turing machine to tweak.
Well, look, let me remind you that this machine, right, has 4 states in it. We've only looked at up to the case. We looked previously at the case of adding a new rule case onto this. You get what I'm saying?
Uh-huh.
But that's not what we're looking at right now. Right?
Right.
What we're looking at right now is the simpler case of, not a known deterministic Turing machine with extra pieces added to it. Okay, as a thought experiment, let's say we took the universal Turing machine and we added extra cruft to it. Then there exists a path.
That one's 3 colors, though.
I know, Ed. The point that I'm making is, how do we recognize, given that we saw that Turing machine, right? And we saw it with all of these different things, right? We'd see one path in the multi-way graph would correspond to the original, more complicated Turing machine.
Right.
I wonder something. I wonder whether there's a signature. If I look here, the old website here, and let's look at this gallery. Okay, there's the head motion. Okay, these are the causal graphs. I don't know whether these are. So the question is, if we made a multi-way causal graph, wait a minute. Turing machines are, am I being confused? Are they always causal invariant because they only have one thing going on at a time? As a non-deterministic Turing machine still causal invariant? I'm not certain. But you see what I'm saying? That this, in this case here, right, you can see that there's something somewhat complicated going on. And if it's a causal invariant multi-way multi-way Turing machine, then each slice of the multi-way causal graph will be the same.
Right.
So, look, we need this, Mano, we need the thing fixed for the multi-way Turing machine, because otherwise, I mean, we could try running this thing here, just for the hell of it. We can try running this, I suppose, as a causal graph. Oh my gosh, what the heck is that showing?
That's the five steps, and everything is eventually going to go to the right, but there's less and less.
I know that, but why is this causal graph showing this kind of behavior? It's looking very much like this, basically.
Mm-hmm.
I don't understand why the causal graph looks like that. This is all the events, all the updating events that could happen. I mean, we go back here. Let's just, for amusement, let's go look at, oops, where is it? Okay. Let's take a look at these samples here, and let's just add in, I'm just going to put in here the causal graph structure as well. Hold on. Not so fast. Let's see how long it takes here. Come on. Some of these causal graphs might get really complicated. For example, for that one, it's probably going to be really complicated. Let's take a look. Render this thing. Oh, great. Disconnected causal graph. My gosh. I don't really understand. So these disconnected causal graphs are a sign disconnected multi-way causal graph means basically that there are events going on over here that can never affect events over here. It's kind of like an extreme version of a cosmological event horizon.
Makes sense.
I mean, right here, there are also black holes because there are events here that cannot affect other events. Once you're one of these events, well, I mean, it will be clearer. Yeah, I mean, this thing here is like a space-like singularity. Your time is stopping in that case.
Mm-hmm.
I don't get really how. Let's see what that looks like. Oh boy. See, it's probably obvious that the structure of these graphs is comparatively similar to the structure of the multiway graphs. That may be obvious. He says, well, that one isn't so obviously similar. Oh dear, I thought this was going to be simple, I have to say, this multiway, I mean, this non-deterministic Turing machine thing. Oh, it just goes to show. Well, I am confused by this, and I think we're depending on Mano to clean up the way this multi-way Turing machine code works.
Yeah.
All right, so just
I'll work on it.
very quickly, let's review Ed's tilings. So Ed, is it trivial to rerun this for the what's it thing, or does that rely on all of this stuff here? Do you understand my question? Ed, hello.
Sorry, I was on mute. It building up the forbidden cases takes a while, but otherwise it's trivial.
Well, no, but I mean, could we run this
For your 5 case?
Yeah.
Yes.
Okay. Can you tell me how to modify this code to run it for that case? Because then what you're saying here, these are the minimum tiling sets that give periodic tilings. You're not showing what periodic tiling they give. Could you generate that easily?
No, not because I'm not generating the tilings. I'm starting with the tilings and I'm finding out what sets they contain. That's much easier. And then
but that's not going to give you. Wait a minute. So you're just enumerating possible tilings, and you're asking what. But that's not going to give you.
It does give you set. It does give you sets you want to avoid. So, for example,
I understand that, but Ed, there could be a set of 3 tiles that tile periodically, but only with period 18 or something, and you're not going to pick that up here, right?
That is possible, but I've ruled it out because I've looked at all the three sets of 3 tiles.
Well, let's take a look here. Let's see. This, I think. Okay. Okay, so here what I'm saying is there are 2 to the 32 possible sets of 5 cross tiles, so to speak, right?
Uh-huh.
Of these, 766 million lead to constraints that can't be satisfied at all.
Uh-huh.
Okay. All right, so I'm sure I say someplace here. Humph. I'm surprised I don't say what the maximum. I mean, look at that one. That has quite complicated. Okay. What is the maximum size of periodic tiling that can be forced? Do you get what I'm saying?
Yes. Interesting question. Because you'd have to avoid all the smaller subsets.
I know. So my prediction is that number is like a busy beaver number.
Click on back to my notebook, and at the top it has the tally length right at the top. The longest I've gotten so far is 20 tiles.
What do you mean by 20 tiles? What does that mean, 20 tiles? What do you mean by that?
That means that the tiling set has there's 20 items in it, and I've got 204 of those.
I don't understand. How could the tiling set have 20 items? I mean, you've only got, how many items are there altogether? There's 2 to the 6.
Right, there's 63 total.
Okay, 64. 64, yes. Okay, you're not understanding what I'm saying, Ed. What I'm saying is, given a tiling, right? Given a, look, here's an example, okay? In principle, oh gosh, it's just unbelievable. In the NKS book, there's, look at that. On the first page here, it says minimal equivalent square tilings, but it doesn't say that on the second page. That's a bug. Maybe Chapin can note that down, please.
Can do.
All right, so this is the set of tilings that we get here. So that's the 171 tilings, okay? And this gives the allowed tiles.
Okay.
So I'm very confused by that representation of the allowed tiles. Oh, this is all allowed tiles. And okay, so hold on. Let's just look at take percent comma 5 all comma allowed tiles. Oh, come on, normal of that. Oh, I see. This is the way I'm representing the allowed tiles with blanks. Okay, so each one of these, so there's a length here. Okay, so that's the number of allowed tiles for that constraint. Now this, what is constraint sequences? And then here's the actual tiling.
Right.
What I'm confused by here I don't know, what do you think this tiling sequence is? Maybe it says in the documentation.
It's probably how subsequent tiles are positioned.
Okay, but so that should tell us what the periodicity of those tilings is, right?
Yes.
So what do we think it is? That's a bug as well. Look at that in5 there. It's just a bug. Okay, so here, let's see. I think that's just this notebook, where it says at the top that the function for generating a tiling from a constraint is also provided. Where is it? Well, that's a question. Chapin, can you note that down, please? Somebody needs to answer that. This claims I wrote this, so I wonder what happened to that function. Somebody removed it somehow. But here, what do you think that tiling sequence means? Or what do you think constraint sequence means? I think what?
I don't know.
Okay, do I have to go look at my source code from 30 years ago? Guess so.
Oh, we've looked at that before.
Okay, well, so what's the answer?
Oh, I still don't know.
Okay, but what I'm telling you is your procedure is not going to work, because your procedure is only going to give you things for which this. So I'm saying, so I mean, let's look at this tiling sequence thing. I have no idea what the tiling sequence thing really does, but
No, my initial code does work. It will tell you if you've got a set of tiles that has any chance of working. generating a tiling from a set of tiles is the next step.
I understand that your code will tell you, okay, so these are the position, these are these offsets, I think, for these tiles, but I don't understand how those offsets work. Do you understand what I'm saying? Okay, I have to go look at my code because apparently this information wasn't preserved properly here. Okay, so let's go look. Page 214.
Oh, that's probably the translation of where repetition occurs.
All right, that's what I suspected, something like that. Chapter 5, Section 7. Let's take a look. Book construction notebooks. Chapter 5, Section 7. It's not very useful. There's a thing called total results. I wonder whether a net contains. See there? That's this thing called tiling data, but let's see, maybe one of these others has. So this is just giving the results here. So results, tiling data, humph. Okay. Put construction data files, no. I wonder whether somebody goofed this up because it says in the description that I gave here, the function for generating and tiling from a constraint is also provided.
I had trouble with putting functions into data repositories because I was told many times they were not allowed.
But you put them in the examples if you have to put them somewhere, or put them in a separate, put them in the function repository.
It didn't exist yet.
Well, it does now.
All right.
Okay, hold on. Let me go back and look for the original. This is called tiling data, book layout results. Book layout results. Chapter 5. Well, okay. There we go. December 1996. That's very modern. I wonder whether what these actually look like. Let's take a look. What one of these looks like. Oh my gosh. What are these? What are these? Those are probably representing some tile set. So this is probably a thing, Ed, why don't I send you this? This is probably a thing that is generating from a tile descriptor. It's generating the actual tiling. Do you think?
Okay.
Yeah, I don't know what. See, there's probably a whole directory full of stuff for generating. I think we found this before for generating But Ed, it's not going to work. I mean, I can already tell you, it's not going to work. Okay, so what you're saying is you look at a periodic tiling and you ask what possible subtiles can occur in that. Is that correct?
Right, and I expanded it out to a pretty big size.
Okay, but hold on. So what does that tell you? If a subtile does occur there, what does it tell you?
That's the tile set that will generate that, say, size 18 block that gets translated over 18.
How do we know that that's the only thing that tile set can generate?
We don't, but we do know that they won't generate anything periodic that's smaller. Because
we don't know that. Okay, so we know that
because basically I built up the periodicity one at a time.
So we know, but we do know what. So you could have drawn what tiling that tile can generate, right?
Yes, if I'd thought when I was generating these, but I didn't. But I can redo it.
Yeah, okay, all right, fine. So we need to know what tilings they will generate up to, but then eventually you can't prove, because it's that given a tile set, it could be the case that a tile set of 22 tiles, let's say, generates a periodic tiling, but only with period 3714.
Right. Mm-hmm.
Right. So the question is to find that. And the way that we're going to find non-periodic ones is when you try to do that.
Well, that's why I have part 2 of my tiling system. Okay.
Which does what?
It looks at the tile set and sees whether they can all cover each other. If basically a tile exists in the set that can't be covered, then it's not a valid tiling set.
Explain that.
So you put down a tile. It has to be able to touch, 8 other tiles in a 2x3 system. And if there is
I get it. If there's a corner that just no other tile matches, then you're toast.
Right. So I've got those 2 checks. And if it's if a tiling set doesn't contain a forbidden subset, and it doesn't...
By forbidden subset, you mean a subset that tiles periodically?
Right.
Okay.
So if it passes those 2 tests, then it could be an interesting tiling system.
Okay, so how many do you have that could be interesting?
None so far. I've looked through millions, and so far I've never found anything.
Hold on. What you're saying is, when you say none, there are 2 to the 64 different cases, right?
Right.
Okay. So
but I've only checked a few million.
I understand that. I'm saying but what you're doing is you're saying of the 2 to the 64, right? You should be able to cut out huge swaths of that 2 to the 64 by these, right? In other words, as soon as any one of these, what you're calling forbidden subsets, of those 2 to the 64, many subsets of the 2 to the the 2 to the 64 represent the subsets of the 64 possible tiles, right?
Right.
So as soon as you get a quotes forbidden set, as you're calling it, nothing that contains that forbidden set could possibly be allowed.
Right.
Okay. So what I'm asking is, of those 2 to the 64, how many of those are now determined to not be possible?
Well, we can eliminate, say, everything that contains a block of all zeros or all ones immediately.
No. But you can eliminate anything that contains, of those 2 to the 64, right? Many, that is a collection of subsets. Right. Any of those subsets for which there is a subset of that subset that corresponds to one of your forbidden sets can be eliminated.
Correct.
Mm-hmm. Okay, so what I'm asking is, given all the forbidden sets that you have found, how many survive out of the 2 to the 64 possibilities?
I don't know.
Okay, so that we need to determine, right?
But look at just 3 tile sets. Not very many of those get eliminated in that set. It's the coverage that kills the sets of size 3.
Okay, well, fine, but either way, I mean, so we're asking. Look, here's the way to do it. Okay, let's consider sets of size 3. Okay, how many sets of size 3 survive as being still candidates?
There's only the first, what is it, 7, 8? 1, 2, 3.
Okay, so wait a minute. Of size 3, there are still tilings where we don't know what it does. Is that true?
Yes.
Okay.
1, 2, 3, 4,
No.
5, 6, 7, 8, 9, 10, 11. There's 11 cases that need to be considered, and then once those are eliminated.
No, but I understand. But you the criteria for eliminating don't eliminate. You don't have a way to eliminate even 3 tile sets.
Yes,
Correct?
basically everything that has on a 0 block or 63 gets eliminated. Everything that has both 7 and 56 gets eliminated.
Okay, I understand. It doesn't matter. I'm saying you have a 3 tile set. You have 11, whatever it was you said, 3 tile sets that have not yet been eliminated, correct?
Right. Mm-hmm.
Okay, so now the question is, what are we going to do with those, right? Because what we had before and what we can get working again is a tiler that goes in the spiral, going out, trying to tile the plane. Am I making sense?
Well, if those 3 tiles can't cover each other, then we know that they won't work anyways.
Ed, assume that you've done all of the tests that you know how to do, right? How many tile sets do you have left over with n tiles for n equals, let's say, 3, 4, 5? So,
right. I've been using this code to try to find one of those, and so far I haven't found any. That's going to be my next set. Once I find
so wait. So
possibly
up to what n have you eliminated them?
I've only gone up to 3 so far, but
Okay,
I've tried random up to 20.
Okay, all right, fine. Fine. So randomly up to 20, everything is failing one of those 2 tests.
Right.
Okay. Okay. Well, that's interesting. Okay, but so what we need to do is so far, even up to size 20 with random, you might as well try larger sizes, larger numbers of tiles randomly. That should be easy to do.
Yes.
I'm
trying to figure out where the best number is, because if it's too large, it'll hit a forbidden subset. If it's too small, it won't cover itself. And I also am thinking I need to add some AI into this or something, so that, say I give it 3 tiles, is there a 4th tile that will not give a forbidden subset but will give coverage?
Oh yeah, I don't think that's going to work. Okay. I think what we're going to need to do, as we did like 25, 30 years ago, is make something which tries to do the tiling using some, backtracking algorithm and so on, right? I don't think we can avoid doing that. Ultimately, we can't avoid doing that. Ultimately, this is a standard, non-deterministic Turing machine problem. Right? And the only way you can do it is by something equivalent to that non-deterministic computation.
Well, if the tiling set can't cover itself, then it's not going to work anyway.
I don't care. We are going to eliminate a bunch that don't work, that whatever. Once we are left over with ones where we don't know if they work or not, we have no choice but to explicitly try making the tiling.
Oh, yes, I agree completely.
Okay, so now the question is, we need code that explicitly tries to make the tiling. You see what I'm saying?
Well, one thing we could just do is giving these tilings that, like that first one there, which in forbidden subsets of size 6, given those 6 tiles, what tiling does it generate?
No. Look, Ed, that's a check. What I keep on saying is, in the end, we need a piece of code that simply goes using, a recursive algorithm, almost certainly, unless there's some clever way to do it. I don't know whether this dancing links technology is useful. I don't know what the right way to do it is. That to find, I'm sort of guessing that in 30 years somebody might have invented a slightly better way to do this. But back 30 years ago, what we were doing is basically just, going out in a spiral and trying to add a tile, seeing if it works. If it doesn't work, you backtrack, et cetera, et cetera, et cetera. Right?
Mm-hmm. Yes.
Okay. So we have code that does that. Although it isn't, it was code that had some crazy interactive component that ran on the next step, in ancient times. So that doesn't work anymore, right? And we're not going to get a next emulator to make it run because it's not really useful. Make sense?
Yes.
Okay. So the question is, what do we do now? And do you know a clever way to do that process of incrementally trying to tile? How do people do this? I mean, this is not, people have tried to do this with polyominoes. People have tried to do this with all kinds of things, right? People did that with polyominoes back in the 1960s with an early computer application.
And usually now it's done with dancing links.
Okay. Do you know how to do it?
Not in Mathematica, but it'd be probably worthwhile to implement that.
Well, but okay, if we've got C code that does it, that would be fine. We just hook it up.
Mm-hmm.
Okay. I mean, do we have code that implements, this is something maybe Max could do, but I'd like to get it actually done. Explain to me how the dancing links method works and how it differs from pure backtrack, recursive.
It works with a linked list.
That sounds extremely similar to what we did before. And I don't know why.
No, it probably is. It probably is. I mean, Danuth developed this decades ago.
To do polyominoes and things, right?
To do all sorts of different recursive searches.
But I mean, is he obsessing about the fact that it's a linked list because he's adding things and subtracting things? Because that's kind of trivial.
I don't know.
Okay. All right. Fine. Well, okay. Rather an unsatisfactory session here. I think a bunch of bugs and things. All right. Well, we should probably wrap it up for now. And yeah. Let's try and get the non-deterministic Turing machines working properly, and then see what's going on with them. Meanwhile, I need to think about the significance of how to think about behavior in non-deterministic systems, which was kind of what I was hoping to get intuition about by looking at these actual non-deterministic Turing machines. And again, by looking at these tiling problems, which again, Ed, we can imagine, okay, dancing links, dancing or not, there is still a multiway system that represents, in a sense, what's happening with the multiway system is you say, what tile could I put in this position? This is, again, I'm trying to get intuition about how these multiway systems work. And in a sense, the issue is, can you get an infinite multiway system out of this tiling. Do you understand what I'm saying?
Yes.
And, you know, if there is a unique tiling, it will be, in the end, a single way system, so to speak. In the end, it will, no, actually, it'll probably be a little bit more complicated than that because there's probably some translational, it's probably unique up to translation. So that will probably add some complexity to it. But essentially, the question is, if there is a sort of higher entropy collection of tilings, where there are many possible tilings, then you'll get a more complicated multi-way system. And what you could also get is a multi-way system which grows for a while, and then the tiling never makes it to the infinite plane. It has a maximum size. Am I making sense? And that will be reflected in the multi-way system. And the maximum size of the tiling would be essentially the number of nodes on the longest path in the multi-way system. Because I think in this interpretation, every node represents, and this is again kind of interesting because this is again one of these local versus global multi-way systems. Every node presumably represents a complete state of the tiling to that point. So
well, let me suggest something. You've got the 19 forbidden subsets of size 1 to 5. Let's look at that last one. And suppose you had the tiling system where we left out 61. There is some largest tiling you could make with those sets, but if you, there are some cases that you won't be able to cover. There's going to be dead ends because you need that last piece for coverage.
wait, to get a periodic tiling, you do?
Yes. There's
Is it
basically
obvious
no
that
way
there's no
to,
other tiling with the four things without the 61? Is it obvious that there's no tiling without the 61? You've established.
yes, because you've got these 3 black bars at the bottom in the first one, and there's no way of covering that. Oh,
Well,
actually,
yes, there is. From the 58.
Which one?
7 and 58 would be.
Oh, it's the second one. White, black, white. There's no way of covering. Oh no, that isn't. It's the third one. Black, white, black. There's only one.
Well, why not? Why not 2 58s?
Because the 58, there's nothing you can put on top of 40. Directly on top of 40.
Okay. But Ed, the logic that you're giving here, I mean, the other thing we might be able to do is to turn those logic statements into something that we could run in a satisfiability solve, in a SAT solver.
Yes, that's what I was thinking. Where if you were given, say, just those 4, it would figure out that this one extra tile is needed, or there might be a set of tiles that are needed.
No, but that's not what I'm saying. What I'm saying is that, well, go ahead, go on.
Oh,
The logic that you are giving could be resolved by a SAT solver, I think.
Mm-hmm.
Although and the issue there is, well, am I right about that? I mean, the question is, if the thing has a tiling, what's going to happen? The SAT solver would say there is, SAT solver could say it will work, but then we might not actually be able to generate a tiling because it's only going to give it's only going to say local matching rules can apply.
Right.
That's your overlaps case.
Mm-hmm. But it gets us farther. It's much better than brute force random. Because you could give it, say, 15 tiles. And if there was a forbidden set involved, it would pick out, okay, if you eliminate this tile, it doesn't contain any forbidden subsets anymore. And then if you add this tile, it has complete coverage. And now you've got an interesting set.
All right, well, so implement that. But I mean, I'm still, in the end, we're not going to get around the fact that we have to have something which simply tries.
Oh, yes. And that's also necessary.
Right.
Yeah, in fact, if I implement that code, then I can just run the code on the forbidden sets and it'll show the tilings they generate.
Okay. All right, I'm going to answer one question was asked by Jonas here about what non-deterministic Turing machines are. A non-deterministic Turing machine is simply a Turing machine where there are, like a case like this, where given that you're in this state, the head is on a white square and is in the up, the head's in a white square and is in the up state. There's more than one possible new configuration that the Turing machine can go into. And that's represented by the fact that this graph that shows what state can evolve to what state is not just a line. So if it was a deterministic Turing machine, it would just be a line. It will be always determined what the next state is. In a non-deterministic Turing machine, it's not determined what the next state is. Now, you might say, oh, let's make the next state be, quotes, random, but that's not what we're doing here. We're looking at all possible next states. And that's what gives us this multiway graph, and that's what gives us all the other things we're doing with non-deterministic Turing machines, is to look at the set of all possible evolutions for all possible sequences of states. All right, we should wrap it up here until another time. And thanks, everybody. See you later.